This is a revision video for GCSE Chemistry about the 7th group of the periodic table, also known as the halogens. By the end of this video, you should be able to locate the halogens in the periodic table, describe trends in their properties, explain why those trends exist, and construct equations to show the reactions of the halogens. The halogens are found in group 7 of the periodic table, on the right-hand side, just before we get to the noble gases. The name halogen means salt former, because when these elements react with metals, they form compounds known as salts, which is another name we give to ionic compounds like sodium chloride or potassium bromide. Most of the halogens are non-metals, and we can tell this because they're found on the right-hand side of the table. Astatine is a metalloid or semi-metal, which means it acts a little like a metal and a little like a non-metal. The halogens are also smelly. Chlorine is one example. And they're poisonous. You probably know already that chlorine is used to sterilise water by killing bacteria, and it can also be used as a chemical weapon to kill people. The first 5 halogens are fluorine, chlorine, bromine, iodine, and astatine. The last element in this group, tennessine, is a synthetic element that doesn't exist in nature, and it was only synthesised for the first time in 2010. It doesn't behave like the other halogens, so we're not going to talk any more about it. The first 4 halogens are useful and important for our everyday lives. Even though fluorine on its own can be quite dangerous, compounds containing fluorine, known as fluorides, can help to prevent tooth decay, and so they're added to toothpaste and also to about 10% of the drinking water in the UK. Chlorine can be used to kill harmful pathogens or bacteria in a process known as sterilisation, so chlorine is added to our drinking water and also to swimming pools. Bromine is used in medicines, drug treatments, dyes, and also compounds which help to make fabrics flameproof. Iodine is an antiseptic used to treat cuts and grazes, but it can also be used as a radioactive tracer in medicine. It can be injected into blood vessels in order to determine where there's a blockage. The halogens are in group 7 of the periodic table because they all have 7 electrons in the outer shell of their atoms. They all form diatomic molecules consisting of 2 atoms with a covalent bond between them. Because these elements all have the same number of electrons in their outer shell, they all form these molecules in the same way. Only chlorine is explicitly named in the GCSE specification, but fluorine and iodine have also been examined in recent years. In each instance, we only show the outer shell electrons, and each of the atoms has 6 electrons of its own and then a shared pair of electrons forming that covalent bond in the centre of the molecule. As we go down the group, the atoms of the halogens get larger, and therefore the molecules that they're being made into get larger. So whereas fluorine has very, very small molecules, astatine has much larger molecules. And so because the molecules are larger, the weak intermolecular force between those molecules also gets stronger. This means that whereas fluorine and chlorine are gases at room temperature, because even the amount of heat that's available at room temperature is enough to overcome those weak intermolecular forces, bromine is a liquid because its forces are slightly stronger and they need slightly more energy to be overcome. And then iodine and astatine are solids. When thinking about the chemical reactions of the group 7 elements and trying to remember which is the most reactive and why, it can be helpful to think of them as almost the opposites of the alkali metals. The alkali metals are the most reactive metals in the periodic table. They lose 1 electron in order to form chemical compounds, and so therefore as you go down the group and they get bigger, they get more reactive because it's easier to lose that electron. The halogens are the most reactive non-metals, so everything is reversed. The halogens do chemical reactions by gaining an electron, and that's easier for a small atom than a large atom. So that means that they get more reactive as you go up the group and the elements get smaller. So fluorine is more reactive than chlorine, and chlorine is more reactive than bromine. And what this means is that the smaller halogens are able to displace the larger ones from compounds. We can show this by reacting solutions of the halogens with solutions of their salts. In this experiment, I filled the wells of the spotting tile with solutions of water as a control, potassium chloride, potassium bromide, and potassium iodide. Then I add the halogen solutions. By comparison with the water control, I can see that chlorine has been able to displace bromine and iodine from their salts, leading to a colour change, while bromine is able to displace iodine. The water control shows me that the colour of the wells on the bottom row is just the result of the iodine that I've added and not a chemical reaction. We can show these reactions using symbol equations. When chlorine reacts with potassium bromide, the chlorine displaces the bromine and takes its place. We form bromine and also potassium chloride. Then we need to balance the equations by using coefficients so that there are the same number of atoms of each type in the reactants on the left and the products on the right. A typical exam question might ask us to describe and explain the difference in reactivity between fluorine and chlorine. So first of all, fluorine, being the smaller halogen, is more reactive than chlorine. This is because it has smaller atoms, or a smaller atomic radius. When fluorine and chlorine react, they do so by attracting an additional electron. That electron experiences more electrostatic attraction to the nucleus of fluorine. This is partly because fluorine has fewer shells. It only has 2, whereas chlorine has 3. This also means that the electron being gained experiences less shielding, which is basically those inner shells of electrons getting in the way and stopping an outer electron from being able to feel the attraction of the nucleus. The halogens also react with metals in quite a spectacular way. We can see this if we observe the reaction of chlorine with sodium. Sodium is a soft, silvery grey metal, and chlorine is a smelly, poisonous green gas. When they react together, they form sodium chloride, which you know is table salt. Let's look at this in action. First, the pale silver sodium is heated with a Bunsen burner until it melts. You can see the characteristic yellow flame that we expect from sodium when it's set on fire. When the sodium is melted, the gas jar of pale green chlorine is added, and there's a much brighter yellow flame. During the reaction, the pale green colour of the chlorine disappears. Afterwards, we can see the white crystals start to form on the sides of the gas jar. If we wait for long enough, these will eventually fall down, and we'll eventually be able to see the white crystals at the bottom as salt. Thanks very much for watching, and don't forget to like and subscribe for more GCSE chemistry videos coming soon.